Hello everyone, distinguished guests, our esteemed colleagues, dear all participants across the globe. A warm and cordial welcome to the inaugural ceremony of the International Workshop of Computational Intelligence 2023. And we are with great pride and honor and it commence the workshop. And the theme of workshop is computational intelligence. So we will think like that. This will make some sense of innovation, adaptation, and progress in through this workshop. And that we can directly go to the inaugural ceremony. I'm inviting Dr. K P Soman for the welcome address. Sir, please, sir.
Okay, thank you. I will. This is visible to you.
Not yet, sir. Arun, can you unshare? Arun. Yeah.
Up now. Now it is
Yes,
visible.
Yeah, it's visible. Yeah.
Okay. Good morning and warm welcome to all the participants. I am honored to introduce our distinguished guest, Professor Mohan Kolhe, Faculty of Engineering and Science, University of Agder, Norway. He is a visionary in engineering and science. His insights and wisdom will undoubtedly enrich our understanding and inspire us to push the boundaries of knowledge further. Today, we are privileged to be joined by renowned scholars, researchers, and industry experts, all united by a shared passion for computational intelligence. Your collective expertise and diverse perspectives are the threads that will drive the engine of innovation throughout this workshop. For the course of the next few days, we have an engaging agenda in store for you. We have meticulously curated a series of enlightening talks and interactive sessions. Thanks to the coordinators, Dr. Ratindraj and Dr. Rahul Sudesh. Okay, these are our experts. Let me hello everybody. Dr. Sunil Matthew, Dr. Krishnendu Guha, Dr. S. Sumitra, Dr. Ram Bilas Pachori, Dr. Arun Sankar MS, Dr. Ibn Deniraj, Dr. Anup PS, Dr. Babalashman, Ms. Uday K. Krishnan, Dr. Minal Kandidas, Dr. Anandanaya, Dr. Devnath Indio, Dr. Devnath, okay, Dr. Soumya. So I'll give a brief intro about probably myself and our the new School of AI. My journey in Amrita started 1996. I joined as a faculty in Amrita Institute of Management. Now it is Amrita School of Business. In 2003, we started a research center. Center name was Center for Computer Engineering and Networking. Now today it is under the School of AI. Previously it was under the School of Engineering. So that time we started with 3 faculty, learned from 3 different departments. Myself from Tupli, Dr. Ramindran Mechanical, Dr. Maleshna EC. Now he is a senior scientist in MPOL. So we start offering Tech in computer engineering and networking. So that time the word IoT was not there, but we had that in mind. Then we proceeded to making our own lecture notes, later got published because this was the first research center of the university. So we need to make the head start. So where it's now our book on now 3rd edition. Data mining got translated into Chinese. One second, okay. Okay. So 2003-5, we had a lot of MS by research fellow. One of the research scholar at that time is now Professor and Director of Amrita Mind Pain Center. He also participated in writing this book. Later now we took a lot of work from ISRO and other DRDO organizations and started publishing research papers. And one other person involved in this is Dr. Sukumaran. Now he is in BAT. He is the top 2% scientist now in the world. Then we took several poets from DAT along with SEDAC Pune. So that was in natural language processing of Indian languages. Then other one task was machine translation. Other was creating all the tools for required for dealing with the Indian language. So it went on from 2008 to 14. So during that period, we could create a lot of experts in NLP, language processing, of especially Dravidian languages. These are the a lot of people participating in this program. Around 2011, our faculty, Dr. Soumya, took up research lead in signal processing and in signal processing, machine learning, and deep learning. So she received a lot of awards, and she was also got award, Gemini AI award. Then we start taking project from industry also. So 2015-18, we got massive funding from Paramount Computers, Dubai, and scholars who were working in that area now become a cybersecurity expert. One of the key person is Dr. Vinay Kumar. Now he is in Prince Mohammed bin for the University of Saudi Arabia. He was here till 2019. Also, another person who established in cybersecurity areas, Dr. Prabhakaran, is now the director, Center for International Studies and Cybersecurity under the university. He got a lot of massive funding from central government, several awards, research excellence award from central government. He has a team of around 150 people working in the cybersecurity area. He is giving software for all the law enforcement agencies in India. Our research results in engagement with international faculty in emerging research areas. Our faculty, Dr. Obalashran, established research collaboration with Professor Jurgen Kurtz, one of the pioneering person in chaos theory and applications. We have some collaboration. We have collaboration across the globe with various universities, IITs and NITs. Then 2019, we started BTech in CSE AI. Till that, we were running only PG courses and research, guiding research. Now, AI is the driving technology for the 21st century. Understanding that one, we started this course with a new kind of pedagogy. We introduced the concept of lab in a pocket. There are many new tools which actually makes conventional labs obsolete, like this now from allowed devices, Adam 1000, 2000, Adam Proto, Adam 3000 extra. So all the electronic experiment can be done now from using a PC in a home or a hostel or in classroom. Now you need a separate lab. Then we had a lot of 3D printers, all these tools. So based on this, we introduced the lab in a pocket concept. And pedagogy, we made every subject project oriented instead of final written examination. We are now giving group projects. Assignment, now we are after ChatGPT, we are taking away assignment portion, mostly in projects and face-to-face evaluation. And we made maths spread over 6 semesters in a spiral fashion. We are teaching all the required mathematics. Since national education policy insists now all our undergrad courses should be multidisciplinary, we have made our syllabus that way. Computational biology, we are offering four semesters. All the basic engineering are taught in the first 2 years, then specialization. So that mode we are moving now. In 2023, that is this year, we started now BTech in AI and data science. So this is basically the history of our center and the new school of AI. So thank you. I once again thank all the participants and experts who are going to give lectures during the next 5 days. Thank you all.
Thank you, sir.
Yes.
Yeah, thank you, sir. For the introduction of our department and also to familiarize all the participants regarding our department activities and all. So I'm requesting Mohan sir to speak some words and please comment on our inaugural address um, to as a to inaugurate our this function in a great manner. Your advice is so valuable, sir. Thank you. Yeah, please, so, thank you.
Thank you,
Mohan sir.
Rahul.
Yeah.
Yeah, it's my pleasure to inaugurate this workshop on computational intelligence. And I believe in this workshop, you people are going to cover many key topics which are relevant in the application of computational intelligence, and especially with focus on sustainable energy technologies. And I observed that while going through the agenda or the program of the workshop, there are very interesting topics in which the participants will learn that how these different computational intelligence techniques can be used for different type of applications. For example, cyber physical systems, or for example, moving towards the industry 4, or making maybe industry 4 standards for cyber physical education system also. And I believe that most of the participants, they are from the academics. So the learning from this workshop will help not only enhancing their personal knowledge, but also it will help to implement that in their teaching or the research also. So when these different computational intelligence techniques are going to be implemented in the teaching or the research, so basically we are going to train the next generation professionals. So that is very important. So Rahul, how much time I have?
5 minutes, sir. 5 to 10 minutes, sir.
Okay,
No
so
issues.
that's
Yeah.
why, because I have one presentation also, but then if I go to through that presentation, it may take more, maybe 15-20 minutes. So that's why I
Yeah.
asked.
Sure,
Okay.
sir. Sure, sir. Sure. Yeah.
So I will not share the presentation because 5 minutes is quite less, or maybe I can just give you a little bit overview. What do you think, Rahul?
Yeah, you can, sir. No issues.
No issue. Okay, then it's fine. So let me give me 1 minute. So can you see my presentation now?
Yes, sir. Yes, sir. Yeah.
So
It's visible.
whether it is coming in the full screen mode or how it is coming?
It is coming in full screen, sir. You can proceed.
So you can see my first screen, right?
Yes, cyber physical systems in higher education. Yeah.
Very good. Yeah. So thank you. and it may take more than 5 minutes, maybe a few more minutes. So, but I will try to
No
be
issues,
very
sir. Please
concise
continue,
and
sir. No
very
issues.
short
Yeah.
because I know we have to respect the time also. So, I was talking about that. This work, the focus of this workshop is in computational intelligence. And this computational intelligence can be used in many applications. So most of the focus has to be that how this computational intelligence to be used in achieving United Nations Sustainable Development Goals, or how we can use all this computational technology for a sustainable development of our society. When we are talking about the sustainable development and when we are talking the use of the computational intelligence techniques, so basically we are talking that we need to move the society to the next level. So, for example, if we want to move our society or the industry to the next level, we have to integrate these computational intelligence techniques in the cyber physical system. And when we are talking about that, and most of the participants, they are from the academic background, so we have to give little focus on higher education also. So in today's keynote speech, I would like to say that how we can use this cyber physical system in higher education and collaborative training for skills development. That focus should be there. Okay, and I believe that the participants, they will love to uh, they would love that how their learning can be improved. So with reference to that, let's say we are talking to move to the next revaluation. So that let's say it is a fourth revaluation, and at this moment we are mainly on the third revaluation. Okay, so in the fourth revaluation, we have to move towards the cyber physical system in which we are going to use the Internet of Things. And this Internet of Things for different type of cyber physical system are going to be controlled by using some computational intelligence. So if we consider this industrial revolution pool, which is going to be there, so in that we have to see that how the learning agility, adaptability, empathy, and multidisciplines are going to be there. If we consider the present industrial level at 3, where we need to have more data expertise and multidiscipline, where we can integrate science, technology, engineering, mathematics together. And when we are talking about the one level below, at that time it was more focus on the business, reducing risk, standardization, and certainty. And if we go earlier there, then it was more on the physical or basic engineering based. So now here, with reference to the cyber physical system, we know that how the computational intelligence techniques are going to work. So it means that we are talking about the industry level 4, in which when we are integrating different type of disciplines or different type of technologies which are available, so for that we have to use this computational intelligence techniques not only from the engineering or the operational point of view, but also in doing appropriate policies also. Yesterday I was reading one article, and that article, it was saying that so around 90% technologies, they are available into the market for achieving the sustainable development goals, are going to contribute towards the net zero. But the big question is that how we are going to integrate them in the intelligent manner, and for that intelligent manner, we need to use this computational intelligence techniques. Not only this computational intelligence techniques for integrating all this technology together, but also developing the appropriate energy policies or appropriate policies at the government level, which can help us to implement or to integrate all these different technologies. So here, let's say I will take you one example. So if we consider the emerging research areas, Just a minute. Why is this? So if we consider this emerging research areas, you will see that there are so many things which are covered in the research area. For example, here I have taken some articles some statistics from the IEEE Explorer. It says that there are so many documents or the research articles, they are available in the different domains. For example,
No, that's noted, sir.
Sir, yeah, sir, you are muted now. Hello, sir. Hello. Hello, sir.
Sir, you are
Hello.
muted, sir.
Hello, Professor.
Mohan, sir. Hello. Hello. Mohan, sir.
Sir, you are muted, sir.
1 minute, sir. I will call.
Dr. Mohan, you are actually muted.
now
Now this okay. Okay. Yes.
Moving now.
yes, it lets me, and now because I think there was some problem, it seems like, but let me try now. Now it's okay.
Okay. Also, slide is not moving.
Shall I do again?
Yeah.
Wait. So the slides are moving now or not?
Slides are not moving, sir.
Yeah. Yeah.
നമുക്ക് പോകാൻ പറ്റുന്നുണ്ട്.
We can move.
Synchronized center. ഇല്ല സാർ റീജോയിൻ ചെയ്യുമായിരിക്കും. 1 minute. Yeah, Mohan, sir. You there?
And now you can see me and hear me.
Yes, sir. Sir,
And
we
you
can
see
move
the
the slide.
slides now.
Yeah, sir.
And now you can see.
Sir, I can move the slide. I think so.
And I can move it. No problem. Don't worry. And now you're in the slide number 3.
Slide number 2.
Industry 4.0.
Not. So
Now here.
No, participants can move. Actually, that slide is.
Can you check it once again?
Yeah. Now we are industry 4.0.
Industry 4.0 sir, now. And
Yes,
third
so it's good. So what was happening, because I think that some people, they are trying to join, so that made me hang on my system, something like that. No problem. So we are on industry 4 slide now.
Yeah, can you change it once, sir, on the 4th slide?
Yeah, now it is 4th. It is okay.
But not okay. It is not moving.
Now.
But I can move, sir. No issues, sir. I can
Okay.
move no to the.
So
you
let's
can
go
visible
on the
fourth
slide
now.
number 4.
Yeah, now it is 4, I think so. Arun, it is fine now.
Yeah, but I guess everybody has to individually move. There is some problem with the settings.
Yes, sir can tell the slide number, then we can move.
Yeah, I am on 4.
Okay. Then you can know, right, Pratiti?
Yeah, I can see now slide number 4. The emerging research area in cyber physics system.
Yeah.
Very good.
Okay,
So
sir,
it means
sir, you
that
can.
we are at
Yeah.
the appropriate place. So I was here and then I think I got muted or we got the hand. Right.
Sir,
So I was talking that when we are talking about the computational intelligence system, so there are a lot of research which have been completed in this area and with from the application point of view. Now it is a time to use that research from implementing into the field or using that research, right, for developing our teaching also or using in the higher education system for training next generation professionals. So here you can see that the technologies which are fueling fourth international revaluation and the articles those are available in IEEE. Here you can see that there are so many articles they are available into the different domain. For example, cybersecurity, augmented reality, big data, autonomous robots, and so on and so forth. So all these research background which have been published in the peer reviewed platforms, for example, IEEE, they can be used in different domains. So here you can see that, for example, we can use in the transportation system, we can use in industrial IoT system, we can use in the healthcare and medical system, and of course, we can use them into the energy system or the smart grid. In energy system, because I have more expertise, I have, or maybe let's say from last 3 decades, I am working in the area of energy system. So I am more competent to speak that how we can use the computational technologies or techniques for doing the or using uh, these for intelligent autonomous operation into the energy systems into the smart grid. So let's move to the next slide. So here you can see that with reference to the previous slide, how this application of cyber physical system in the smart energy systems can be done. Let's say we can use for the energy conversion control, we can use for the power system, power generation, we can use for the protection system also, we can use for the hybrid control, battery management system, wide area monitoring, microgrid, power system control, cyber security, onboard power system, modular converters, and of course some communication protocols which are going to be required for using all these computational intelligence techniques for doing the operation of smart energy system. So with reference to that, I would like to just share one small experience of mine working in one of the European project in which we used these different computational technologies for developing this cyber physical system for intelligent operation of scalable energy management infrastructure for aggregation of households. And the target outcome of this project, it was that how we can use ICT infrastructure for controlling or for managing the electricity consumption of the selected non-critical power intensive load, considering the incentive-based demand response program. So here in this project, I would like to, Rahul, can you move my next slide?
it's the
Hello.
sixth one, right, sir?
Let's go on the seventh number slide.
But the slide, it's entered, I think so. Can you reshare it 1 second, sir?
Yeah, I will do that. Don't worry. So now it is there.
Yes, it is there, sir. Yeah, it is moving also. It is fine now.
Moving.
Yeah, it is moving
Obviously.
from your side. It's visible now. Yeah.
Let me see. Because sometimes
Yeah.
it happens. I know.
No issues,
So
sir. No
no
issues.
problem.
Listen.
Because it sometimes like so Microsoft doesn't like to.
No issues, sir. Please continue, sir. No issues.
Yeah, no problem. So So anyway, so what I was going to tell you, because we have the limited time also. So that this in within this cyber physical system, when we are talking about the computational intelligence technique, I was planning to share with you the experience of mine working in one of the field project in which we tested this intelligent system for doing autonomous operation of demand side management for shifting the operation of non-critical power intensive load, selected load, right, for reducing the peak demand on the network, at the same time facilitating renewable energy integration. So in this project, it was looking like a very simple project where we want to shift the demand, but when we want to implement that, we need to use a lot of computational intelligence techniques. So for example, let's say when we are talking about the centralized operation of shifting the load, right? So of course, then we have to consider the virtual power plant approach. And when we are talking about the virtual power plant approach, we have to use different type of computational intelligence techniques. For example, we need to have the demand prediction. We need to have the renewable energy prediction also. And of course, the energy market, that is also going to play the very major role. So based on the energy market prediction, based on the demand prediction, based on the renewable energy production prediction, then centralized virtual power plant has to make the decision that which type of selected non-critical power intensive load has to be shipped, right? So for that, this computational intelligence algorithm are going to design or develop the demand side management scenario, let's say for next 1 hour, 1 hour or couple of hours. And based on that, that centralized virtual power plant uh, system is going to communicate that signals to the individual houses for shifting the operation. Okay, so that was the real project which was implemented in the Norway as well as in Switzerland for 100 houses. So here you can see that when the centralized virtual power plant, which was located into the Germany and for this project, it was doing all this computational intelligence based on all the data which have been collected, and then those information were communicated to these individual houses within the Norway and within the Switzerland for shifting the operation of non-critical power intensive load. So of course, then it has to use some communication method. So we in that project 3G communication have been used, but now we are talking about the 5G. You can use the 5G also. So now the question is that the signals which are coming from the virtual power plant to this home, it has to be completely cyber secure also. Otherwise, someone will be in a position to hack that one also. And then accordingly, we have to shift the operation of that particular load. Right. And then, of course, when that signal is coming to the smart meter, and within that smart meter, then again it is going to communicate with the local load. So that local communication, it may be through the Zigbee or local Wi-Fi or maybe another thing. But in this project, it was through the Zigbee. And then, of course, one has to consider the user behavior also. So all those points are quite interesting and important to understand. I think now the slides are moving. I hope so, right? So here you can see that there were a lot of industry partners and academic partners also. So what I want to say that in this course, I strongly believe that you will be in a position to learn different computational fundamentals of different computational intelligence techniques. And I believe that the learning from this workshop are going to be useful for developing your skills and using that skills for doing the higher education. So maybe in a simple way, I can say that this workshop may help you to train the trainers, and then you will train the next generation professionals in your academics or in your teaching those courses, or maybe in doing the research work. Okay, so it seems there is some little bit problem with our system. So I will stop here, but maybe at some point we can have more further discussion on how we can use the cyber physical systems, especially in the higher education, And of course, taking a typical example, which I am going to, which I have planned to share with you, but due to this technical difficulties, we are running out of time, so I will stop here. So thank you very much, and I wish all the best for the participants to have effective learning. And of course, the important thing is that you have to use this learning in your education, teaching, and the research also. So thank you.
Thank you, sir. Thanks a lot for your valuable words and valuable suggestions, and for inaugurating this international workshop. Shall we have a snapshot before the vote of thanks? Soman, sir, you there?
Yes, yes.
Yeah, sir. Mohan, sir, can you unshare your screen, sir, once?
Yes, that's what I was looking now. It stopped now.
Not that. Yeah, it's stopped, sir. Yeah, I will take a snap now. Minute. Yeah, ma'am. Deepa, ma'am, you can also join.
It seems we have a lot of participants. I can see 165 people are there.
Yeah.
So it's really good. So
1
we are
minute.
training the 165 people, and of course, then most of them will go into the education sector or maybe in the doing the research. So that's really good. So it will be very good
The
impact
interesting thing
on
is
the
actually the
outcomes.
most of the equal amount of students, faculties are there for the participation registration itself. So I think it will be a great learning for all of us. Uh, yep. Thank you, sir. I'm inviting Dr. Arun K. Raj, research track of School of AI, to deliver his vote of thanks to uh, our guests and the participants. Yeah, please, please, Arun.
Yeah, thank you, Rahul. So, first of all, a big thanks to Dr. Soman sir as well as Dr. Professor Mohan sir for chairing the session as well as for
Arun, few noise
no problem.
came.
I have muted the participant. Yeah, so
Participant, can you mute your mic and video once? Wait, Arun, 1 minute. I will check. Yeah,
yeah, I have muted
yeah,
them.
yeah. Now audible, I will. Please, Arun.
Yeah. So thank you, Professor Mohan sir, as well as Professor Soman sir for giving an inaugural address, as well as to chairing the initial welcome address for our international workshop on computational intelligence 2023. So, Professor Soman sir actually gave a big introduction about our department, which was CEN, Computational Engineering and Networking Center, which is now renamed as the Amrita School of Artificial Intelligence. We have expertise, we have a strong expertise over the last 20 years in the field of AI and data science, and we have 2 DTech programs and 1 MTech program in data science, which is currently running. And also we have several other PhD scholars. So this was PhD scholars and postdoc that is working under us on various industrial and government sponsored projects as well. So we have very good collaborative network, which is from national as well as international, from academia as well as from the industries. This was an overview which is about our center, which was mentioned by Soman sir in the inaugural address. Then later on, Professor Mohan told about the various areas in which cyber physical systems applications are. for example, in higher education, and how it will lead to collaborative training for skill development. So he was mentioning his own experience while doing similar work funded by the European Union, as well as based on the articles and based on the science articles that is read, based on how it is important that we should all work for sustainable development goals. So that was a part of his talk. And also, I would like to thank University of Agder, because they have already an MOU with Amrita University. I guess they are currently working with electrical department. I guess so, if it is right. So I have already a well-established MOU with our campus. And last but not the least, very much thank this have to say, because I guess it is quite very early morning in Agder, Norway. So thanks for your time. Like, you readily agreed, even though it is very early morning, you agreed to give. You agreed to be the chief guest for our international workshop on computational. So thanks a lot from on behalf of Amrita University and from the Amrita School of AI. And for all the participants, we on the next coming days, we have curated some of the sessions in such a way that you get an exposure to almost all the areas in engineering and life sciences where you can apply AI, and also you can learn about more about AI and data science, or machine learning and data science. I hope you all will enjoy the sessions that we have curated for you, and I hope you will enjoy all the sessions. Thank you.
Good, thank you.
Thank you, Arun. Thank you, sir. Thanks a lot. Thanks
All
all
the best,
participants.
okay?
Thank you, sir. You
And
too,
all the
sir.
best to the
can-
participants also. Thank you.
Thank you, sir.
Yeah, because we have some technical problem. Otherwise, it might have been very interesting to share some of my work with you.
Online.
But
Sure,
no
sir.
problem.
Definitely.
We will do next time. Okay.
Yes, sir. Sure. Thank you.
Very good. Okay. Thank you.
Thank you.
Thank you.
Thank you, sir.
Take care. Bye bye.
Thank you. Yeah. Bye-bye. And participants, please hold this meeting link itself. First session will start at 9:30 from Professor KP Soman, sir. Yeah, we can hold it for a 2 minutes break, and we'll come back at 9:30. Thank you. Participants, please mute your video and audio. And for every session, we have a 10 minutes QA at the end of the session. And please make it useful for your interaction with the speaker, and write your queries in the chat box. An attendance form will be issued in the middle of the session, and we can you just enter your participant ID, your name, and your part of which organization that you can mention in the attendance sheet. Okay. And after this all the session, we will provide that feedback link for an email itself. Thank you. Yeah, we can start the session, sir.
Can start now.
Yes, sir. Yes, sir. Please, sir.
And
Yeah.
the screen is visible.
Yes, sir. Can you make it full screen, sir? Yeah, perfect, sir. Thank you.
So video are not using for some places are not get the full bandwidth. It's okay. I will just use audio only.
Yeah, it is now going
Okay.
good. So
Once again, I hope audio is on. Okay. Welcome to the first session. My talk is on data science and dynamic mode decomposition. To understand what data science is, I'll take a very small sample first. Then we'll proceed. The first data scientist is basically Kepler. He collected thousands of years of data on stars and planet position from sailors, and based on that data, he made his Kepler's laws of planetary motion. And later, after 50 years, Newton discovered or derived equations of dynamics, for which he had to invent calculus. So from data, he derived the differential equation followed by the motion of planets and all the other laws of motion. So basically, now in what in data science we are doing is, given the data, which we can think of as solution of a differential equation. Okay, can we find the differential equation? What we are given is solution. For example, planetary motion, it follows differential equation. What we observed is planetary motion position. The position at different time, xt, yt, zt, and probably its velocity. Okay, given that one, can we find the differential equation? This is one of the problem we solve in data science. That is given the output, the output sequence or data values of variable of a dynamic system. Can we find governing equation? Okay, dynamic here in the sense the state variables. Here now in case of planetary motion, position is continuously changing. Position and velocities, and also velocity might be continuously changing, and therefore it constitutes a dynamic system. So can we find the governing equation? Okay, so in a sense, there is a reversal. In usually in mathematics, we learn how to formulate differential equation based on physical laws, and we solve it. And this is data science is just reverse. From the data, get the differential equation. I hope we understand the difference. So, so data science as such, as we understand now, it is not a new science. It is really, really old one, but the scale has increased like anything. Okay. So Newton dealt with only a few variables. Now we are dealing with the millions of variables. So that is difference. And dynamic mode decomposition is exactly doing that one. For which we need little bit advanced linear algebra and optimization techniques. And of course, computing power. So to understand further, we'll take a simple example, which you cannot solve by hand, though it is an extremely simple problem. Okay. Velocity of a falling body under a drag force. So there is gravitation and also a drag force. When it is falling down, proportional to velocity, there is a upward force. Then given velocity profile, can we generate governing differential equation? Okay, instead of a simple example, now high school level example we can consider. Okay, so this drag force experiment, physicists or physics people have found out that now this drag force is proportional to square of the velocity, and also other things like shape, density of air, etc. Okay, so finally most of them become constant. F drag is now proportional to v square. We can take that one. Okay, and this is taken now, example is taken from the book Computational Calculus by William Flannery, very famous book from Berkeley School. Okay. Assume we need to solve the following differential equation. It corresponds to the following object. That's all. So this is now, since it is a nonlinear equation, nonlinear differential equation. Okay. Usually now nonlinear differential equation is not. We usually will not have analytical solution. Usually, finding analytical solution is a really tough task because of now this nonlinearity. dVt by dt equal to -1 due to gravity and plus 0.01, that is the constant, into Vt square. And we assume now some kilometer away, some object is there, it is falling down. Initial velocity is equal to 0, just dropping. Okay, so many practical problems now, this is the case where you don't have analytical solution. There is no this one. We have all the equations like v equal u plus RT, distance traveled s equal ut plus alpha t square, all assume. Okay, only one, I think it's a force there, that is a force due to gravity. This one now, this buoyancy is not considered. Once it's considered, it becomes a nonlinear equation. You don't have analytical solution. Okay, and from here we can also infer immediately that when velocity Vt equal to 100, 100 and 100, to cancel this this -10. Okay, so when velocity becomes 100, your rate of change of velocity become 0. Note this one, 0.001. Say 100 into 100, the whole become plus 10. This portion become plus 10 and cancel out. Okay, finally now the falling body attains a constant velocity. Okay, so this is the actual solution now. Finally, should be happen that way. Now, this we can solve quite easily now using Euler method. Okay, assuming some position, the position say 10 kilometer away in the don't say above the ground, initial velocity equal to 0, time equal to 0, p equal to initial position equal to this one. This one now very easy to numerically solve this one. Analytical solution is very tough. Numerically, we can easily solve this one. Okay, we can solve in MATLAB. We can solve this one by assuming now for a small delta t period, our velocity and acceleration already constant. Acceleration due to gravity is constant, but this velocity change and total acceleration. I can say here this will change. Actually, the gravity remains same, but because of this upward buoyancy, this effective acceleration will go on change. Okay, so this can be easily solved. I'm not going to details of the solution methodology, but this is what is solved in MATLAB. Okay, what is negative velocity? When velocity become around this is the time velocity. Okay, velocity become 100. Okay, this velocity is not further not changing. Negative velocity is spotted because falling down velocity is negative and going up velocity is negative. The convention we use. Okay, so this is what has happened. Okay, when velocity reaches 100 now, further velocity is not changing. But as per our formula, Okay, as per our formula, V equal to U plus RT, it will continuously change. But this is a real situation. If we can solve, then solve this in spreadsheet also quite easy to solve. This is one thing now, new generation students and also the faculty to understand is that right from school level, we should start solving differential equation. We should never assume, okay, everything is linear analytical solution. But since computing power is there, it is quite easy to solve. Spreadsheet will do. Okay, we don't have to remember anything. How to what we require is only discretization of the differential equation. This is quite simple. So that way we can solve it. Suppose now we take the case now. Somebody has given this velocity profile, okay, or that object. Assume somehow we have measured. Let's assume now some sensors, laser-based sensors. Now we can measure the velocity of the falling object. Suppose that we have. Can we recreate now differential equation, weight differential equation, for which, okay, all of you all know this one. So basic requirement is now linear algebra. The interpretation of A is equal to B. X is unknown. A is equal to B we are solving. Okay, and this X equal to B. How much two interpretation actually? This is A is a this for interpretation actually. I'm telling. So these are metrics and these are the coefficients AX, X1, S2, S3, S4. So one interpretation linear combination is very important. Okay, this left side is equal to this in the first column linear combination of column vectors. Another interpretation is now when you have the right hand side A and X, you are taking dot product, assuming X is known. X1, S2, S3, S4 is known. Okay, so two interpretation of now matrix vector product is very important actually. This dot this row vector dot column vector equal to this. So two interpretation is very important when you proceed. Okay, now we formulate the problem. Okay, you are given velocity, okay, at different times t equal to 0 to, okay, for a period till now reaches the ground. We are continuously noting as a equal interval now velocity. So velocity is given. Our aim is to find out, okay, what differential equation this falling body follows. Okay, so V dash t equal to -1 this one. Assume now this relation is not known. What we know is only V of t. Can we somehow get V dash t equal to this the one now the system is following? So this is basically now the essence of data science. From the data, get the model. Model conventional statistics and now the type of conventional thing usually go for regression type of equation. Of course, here also regression is happening, but here finally we are finding the differential equation. From the data, get the differential equation. Okay, so if Vt is known at different time t, now we can immediately find out now its velocity at a different this one. So for example, V dash 0 equal to V of delta t minus V of 0 divided by delta t. Like that now. So this 0 corresponds to 0 delta t, 1 corresponds to 1 delta t, n corresponds to n delta t. Okay, take it that way. Okay, so we assume t versus Vt values are known. From this, we'll create a dictionary of column vectors. Note this one. This is a column of ones. Then a velocity. You can each velocity can square and put as a vector q. Okay, so we are creating a dictionary based on the velocity. Okay, so probably we'll be using our own basic understanding of the problem in this by creating the dictionary because we don't have any prior idea in general, but some cases we have based on our intuition we can create. So for example, here V dash t may be of the form C0 constant, nonlinear regression form C0, C1 Vt, C2 Vt, V square t, C3 V cube t. And the assumption we are making is now usually a natural system now. This usually goes second order or third order structure. We won't go beyond that one. Okay, so we create this one. So your velocity V dash is here, unknown quantity. Since Vt is known, this dictionary we can make. Now unknown quantities now C0, C1, C2, C3, etc. Okay, our case we are taking this. This dictionary matrix. Okay, one more thing is important here. Now data values are delta t apart. So 0 means 0 delta t, 1 delta t, n delta t, and everywhere 1 is that actually means 1 delta t, n means n delta t. So from B we can create now this dictionary. Okay, so B dash this one. So this we have to get. Now comes the dictionary. We can put any number of things. Now very important thing, next one. How to choose the right term from the matrix. For example, here V dash velocity t actually depend upon in this case when you use on a C0 should be equal to -10 and V square t V square, this is the third column, correspondingly C2 must be equal to this is what we are supposed to get. Okay, so challenge how to choose the right column from the matrix. V dash t may depend only on very few columns in dictionary matrix A. So this the place where now we have to use some advanced mathematics. Okay, so concept of now sparse solution for Gaussian elimination, we can use that one. For example, MATLAB x is equal to a backslash b. Okay, if x will be as infinite solution, okay, we can get a sparse solution possible now. X is equal to a backslash b, but the real theoretical way, if you look at, we are supposed to use something called L1 norm optimization theory. Least absolute value optimization theory. If you are using norm, we will get a sparse solution. That is now this system equation have many solutions. Get the sparsest solution possible. Okay, so if you do this one on I can say in MATLAB, okay, a backslash b, okay, actually it is retrieving recurred coefficients. I given only Vt, and it is telling us C1, C2, C3, C4, C1 equal to -10, for C0 equal to -10. This is C1, this is C2, C3. Coefficient of now Vt into Vt is 0, 0, 1, 0. So actually my created data, the created data is actually this 0.001. Okay, that exactly is we are now getting back. Other two questions are 0. Okay, so from a velocity profile, okay, we could create now differentiation. Okay, differentiation now based on this 4 coefficients. Now you can write out your differentiation. It is nothing but this one -10 plus this one. Okay, so this is the simplest example I can think of. Given data, get the differentiation. Okay, you may doubt regarding now only one thing, whether how to create this dictionaries, what term we should include extra. But theoretically you can take as many columns as now you want. Okay, then try to get a sparse solution. Usually that will be your differentiation model followed by the data. Okay, now this idea can be extended to complex dynamical systems. Already a lot of work has gone into this domain, and one provided by there is one great professor in Washington University, J. Nathan Kutz and team. Okay, so they are the one first to can say apply this. Okay, they get not this Lawrence now the system, which is basically a small model of the weather. So dx by dt equal to sigma into y minus x, actually y of t minus x of t. So this we call also it's a coupled differential equation. Okay, so if this data, if you are not by you solve this one, create x of t, y of t, z of t. This is the differential equation. Suppose you solve with some initial condition. Okay, so get x of t, y of t, z of t. If only that is now given to somebody, okay, we can in fact recreate now this differential equation. We can find out. So you solve this differential equation. For example, suppose you are solving differential equation using MATLAB. Give me s of t, y of t, z of t for that series you give to me. Okay, for example, this s of t, y of t, z of t. Then now I can tell which differential equation now you have solved. So this is called now sparse identification of nonlinear system. This is called SNT. Code is available internet. Okay, simply write sparse identification of nonlinear system. So idea simple again. X of t, x dot t, that is not dx by dt, dy by dt is t. This is the one you can create from x of t, y of t, z of t. So when you solve this one now, we are getting x vector, y vector, z vector for different time. That is x of t, y of t, z of t. This is called x of t. From this one now, knowing the delta t used in the differential equation solution. Now, when you solve this one, you get delta t. Okay, you can immediately create s dot t, y dot t, z dot t. Difference between dx by dt, dy by dt, dz by dt. You can recreate from this one. Then you create other thing, s square t, x t by t, x t z t, y square t extra. How big a dictionary you create? Okay, then you try to get this solve this one. So there are multiple equations here. But we can easily solve for this dx by dt alone using dictionary, dy by dt alone using this again same dictionary. Then the coefficient will be come here, come like this. So you can search internet for this. Code is available. Okay, we can finally not give exact no, this sigma whatever this one now the term will take out. For example, dx by dt this blue one. You can see only two coefficients here that correspond to now sigma y minus sigma x, sigma into y of t minus sigma into x of t. Okay, so here the solution portion now finally solved, you get only two coefficients. When you solve this one dy by dt now, you will get three coefficients correspond to this. When you solve dz by dt here, when you solve this one with respect to this dictionary, okay, you will get now two coefficients. One correspond to z term, z of t, and x d by t. Okay, only two coefficient you will get. So only thing is now you should use concept of sparsity. Try to express using minimal number of basis vectors in this I can say dictionary. Okay, this is the idea. Okay, so here only finite number of variables which you can easily solve. So this give you some idea about now what data science is all about. Basic data science, but it is a very simple example. Okay, then people extended, not going into details of this one. People extended this for nonlinear system. It's also nonlinear. Okay, nonlinear no differentiation, partial differentiation people have got discovering PDEs. Okay, to the 17. So this is the fluid flow across a or a cylinder. If the data is over time is available, we can in fact discover Navier-Stokes equation is possible. Okay. So these details are not going. We can just type the word discovering PDs, and this team, this Kurtz, Nathan Kurtz, Brendan, the two famous Steve Brendan and Nathan Kurtz, J. Nathan Kurtz. It's a extremely good group working in this area. Okay, so these are the type of partial differentiation they are solved using this technique. Extremely simple. The only thing is you should know how to find out sparse solution for a equation of type now Ax is equal to B. If Ax equal to B has infinite solution, how to get the sparsest solution? In fact, that idea is borrowed from another area called now compressed sensing, which came into be existence now with the theory started now 2005 to 8 period, 2005 to 8 period, something called compressed sensing. So from there only the idea is taken. Okay. Okay. Now I am going for another, before going to DMD now, another very interesting application of what I have taken so far, exact frequency estimation. Let me see this 1 second. Okay. exact frequency estimation. If anybody have any doubt regarding, sorry, not doubt, any question regarding this one, can somebody can tell me that interrupt and tell me. Or at the end, you can. The exact frequency estimation. Okay, based on the same technique. So frequency estimation usually we learn, okay, for a series, for a transform, etc. But okay, using the methodology taken so far now, we can get exact frequency estimation. So we'll go that one, starting from a differentiation. So a little bit about exact frequency estimation without this term. So spectral estimation. Now it is a data science tool. It's extremely important in many areas of science and technology. Usually EC branch. Okay, they go deep into this one. Computer science and other well, okay, they have applications, but electronics and communication, terms of branch, terms of faculty influence only use it maximum. Okay, anyhow, there is something called now spectral leakage. Idea is this: suppose now you have a signal with the 50 point frequency, now single frequency, singleton frequency 50.0015 or 50.1. If you take FFT of this one, by taking a small data, okay, you won't see a FFT won't tell no, actually signal contain only single frequency. It will say so many frequencies. Okay, we call this as spectral leakage. There is a basic linear algebra reason for that one, why it happens. Okay, and for exact frequency, there are different methods. Cornish method, Newspeak, etc. We are not going to any of this one because require higher level mathematics. That's now basic high school mathematics, how to get okay result now what obtainable by all these classical methods. Okay, I directly go into solution methodology. Okay, now this one exact frequency. If there is a signal, if you are generating now some single tone, several multi-tone signal. Okay, if you give the data to me, I can exactly tell the frequency. Okay, without any what I can say. Instead of one frequency, I won't tell no multiple frequency. It contains only one frequency, also only one frequency is there. Okay, but you use FFT with the finite number of data, it will tell. Okay, signal contain multiple frequency. So how it is now data science solve this problem. So consider this one differentiation. D square by b and t by t by dt square plus omega square by t equal to 0. We call this as autonomous system. This system with some initial condition. By your 0 equal to something. Okay, there is no input to the system. System should drive its own based on the initial condition. Okay, consider this one. Okay, this is actually solution correspond to now. Solution will be something of this format. Okay, sin omega t or now cos omega t extra. So considering now, of course, here I have taken sin t plus 5, actually it is sin omega t plus 5. Its solution will be of that format. Okay. So I'm going to, okay, I think say write this into a special format. Okay, that involve metrics. Okay, this equation converted now to two equations actually. One is this one d by dt equal to 1 into dy by dt. Note this one. So this is called sort of now state equation. D by dt equal to 0 into by t, 1 into d by dt, and d square by dt equal to minus omega square by t. That is actual this one. Okay, and 0 into this one. So we can write the equation like this: y dash equal to ay. This is a starting point. I don't know undergraduate level. This is taught that way. Okay, so we have a matrix here. This matrix is going to play extremely important role in future DMD. This one. You get a full idea about dynamo decomposition from here. So y dash t, y dash is this one, ay. So the solution for this autonomous equation is given by this: e power at y0 equal to yt. Autonomous because there is no input to the system. System is driving based on this initial values or initial energy in the system. So this is going to be the solution for this one. undergraduate level now, we are learning the control system now. Usually, the control system portion only we are learning this equation. People also call this as now state transition matrix, E power t. Okay, so E power t, E power. Okay, this is actually a matrix only. A matrix into y0 equal to yt. I explain what is E power t is. So now y of 0 is you put here y of this one y of 0, y dash 0, that is y of 0, because your variables are yt and dy by dt in this y. So t equal to 0, y of 0 into dy by this one. So this is the your solution. Okay, yt, y dash t. So this your state variable at any time t. By t and y dash t is given by e power t into this. And probably you can write this on the left hand side. By t equal e power t by 0. Okay, probably that is better. By t right on the left hand side. So by t equal to this one. So knowing the y0, t equal to 0 state variable, you can find out now state variable at any time t. So we call, because of that one, we call this as e power t state transition matrix. So e power t is a 2 by 2 matrix, which can be easily obtained using this matrix A's. Okay, eigenvectors and eigenvalues. So basically, e power is nothing but now this only. S is a eigenvector matrix. In our case, our A is now our 2 by 2 matrix only. Because of that one, this e power lambda t per lambda t. So this correspond to lambda 1 lambda 2. Okay, correspond to eigenvalue of the matrix now A. A is nothing but now this one. Its eigenvalue will come here as lambda 1. So now for this particular system, now you will get only lambda 1 as plus I omega, lambda 2 as now minus I omega. Okay. So when you expand this one now, finally, if you expand this one, this e power t is a matrix whose eigenvalues are e power lambda t extra, lambda 1 equal I omega, lambda 1 imply that now angular frequency oscillation is now. So based on this one, you are getting the solution. Okay. You are able to abstract now. We can start once you know this matrix A. Okay, matrix A will contain the frequency of this oscillation. That is the basic idea. Now, we suppose you have only data. Yt is a single tone sinusoidal oscillation of the form from A sin t plus B cos t. Now we are sampling this function. Yt equal to. Okay, your aim is right out now. What is a frequency content of what is now your aim is to understand. Suppose this A sin omega t plus B. What is that omega? Okay, what you are giving me is only Yt at different time. Okay, so now how to get that one? Okay, so listen carefully how to get now this omega. So on sampling the state variable at t, e power t y0 y dash 0 equal to yt y dash t. Okay, and put in t equal to 1 delta t. We obtain this t you replace by now 1 delta t. So e power delta t y of 0 y dash 0 you can interpret this way by 1 delta t minus y0 divided by delta t. 1 correspond to 1 delta t only. Okay, right hand side yt. Okay, so t equal to 1 delta t of put. So this becomes now y of 1. 1 actually correspond to 1 delta t. So y dash t you put like this by 2 minus by 2 means by 2 delta t minus 1 delta t, 1 delta t divided by delta t. Okay, where by k, because now when you program, you can't write index as a fraction. Index, your index of a variable should be only integer. But from the context, you should understand y1 actually correspond to 1 delta t, 0 corresponds to 0 delta t. Now, consider now this p, okay, as e power delta t. Okay. So what are these? I am naming it as b. Is such that y0, you can think these are metrics now. These are metrics maps y0 to y1. And based on the second one, we can now this y1 minus y0 divided by delta t should be mapped to y2 minus this one. So this should happen now. If this is a solution, okay, this should happen. Basically, that means y1 minus y0 should be mapped to y2 minus y1 because delta t is there both sides. So this B has a very special property. Matrix has a very special property. Okay, finally, okay, y0 should map to y1. Here, y1 minus y equal to y2 minus y1. Okay, and y0 finally originate this here according to this one, it should be mapped to y0, it should be mapped to y1. Okay, so for this to be true, y1 should be mapped to y2. That means now this matrix e power delta t such that y0 should be mapped to y1, y1 should be mapped to y2. That is, you get this relation. E power t as a matrix should map y0 to y1, y1 to y2. Okay, so in general, that matrix should map yk to yk plus 1, yk plus 1 to map to y of k plus 2. Okay, so to get a good estimate, what you are going to do is we create from our sampled values, data values. Now we are creating now these pairs y1, y2, y2, y3, etc. And another one, taking the you take the second column onwards, we take, okay, and you extend the last column like this. So finally now, what now why are getting so many? This one is we want to get a good estimate of, okay, this B. So assume now B is unknown. You should map like this. Okay, so y1, y2 should be mapped to y2, y3. y2, y3 should be mapped to y3, y4. These are our requirements. So the requirement now reduces to assume B is unknown. So now assume now your matrix E per delta T is unknown. We are given only data. Okay, suppose now MATLAB your index start from 0. Your data y1 to yn. Okay, assume now you have sampled this function intervals of delta T. Okay, so from this data, note this one, I'm not using Fourier series or Fourier transform anything to get the frequency. You are giving me now this you can do. I'll explain the codes. Sin omega t, you are sampling. Okay, you are giving me the data. Okay, from data I'm making now two matrices x and x augmented. Okay, augmented x augmented this one x augmented 1. It's a shifted version of this. Okay, now what we are finding is now a matrix A, which is actually your e power delta t. Your aim is to find that one. Okay, which maps this one to this. Okay, which you can easily obtain using pseudo inverse. Okay, note this one now is sort of a regression. Okay, least square solution. You can think of that because now y1, y2 should be mapped to y2, y3. y2, y3 should be mapped to y3, y4. This should be mapped to this one. So to match everything, we are going for a least square solution. In fact, pseudo inverse gives such a solution. B equal to. Okay, this stands for now pseudo inverse. So now this B is actually e power a delta t. So eigenvalues of B contain information gotten of frequency oscillation. Only thing is now we should be thorough with the pseudo inverse. I don't know whether I am or okay. Idea is simple. So I'll revise this way. You sample a signal. Say sin omega t plus phi can be anything. Give to me. The data alone you give to me. Don't tell me what frequency you have taken. Finally, now you can give me few samples, say a few sin omega t, cos omega t in a different frequency. Okay, and sample and give to me by adding sync to me. I will tell you exact frequency which you are used without using any Fourier transform or anything. So that is the basic idea. This is data science. So now, okay, so after getting this B, okay, so B is equal to, now you can say now B is exactly equal to e power a, actually stand for e power a delta t. Okay, so this e power a delta t corresponding eigenvalues of that matrix, okay, will be e power lambda t extra. So I can take out now, I can find out this lambda 1, lambda 2. That is a basic idea. I'll give the part here now, don't worry. Finally, I'll say from B, I can get the frequency oscillation. Now, this is a prelude to DMD. DMD uses, but your matrix here is E power a delta t or B is not 2 by 2 only, our case. Okay. But in real situation now can be very big matrix with a low rank. Okay. So in DMD, what we are doing is, I'm not going to, DMD will be taken it later. Okay. One more operation is, okay, we are doing, okay, especially when B is very large matrix with a low rank. Okay. So one more operation. So B equal to your expansion goes like this based on center value decomposition of your this matrix pseudo inverse. Okay. I am assuming now this sigma is whatever this is invertible. 2 by 2 matrix is invertible. Our case. Okay. So if it is not invertible now, it should be pseudo inverse. V is nice. Okay. I'm not going to too much detail in this one, but now a low rank matrix B tilde is possible. If this B is very large matrix with a low rank, we'll be creating a as similar matrix from here. So B equal to this. So from U Hermitian, you take now this left hand side. So BU equal to from here like this. Then now you take U Hermitian BU or now U transpose BU. Okay, create that one. Something like this you will get. So this B tilt usually, if B is a very large matrix, okay, and a low rank, if rank is R, from U now you'll be taking only this similar value decomposition, R columns only. So this will be a small matrix. Okay, so this small matrix, okay, eigenvalue you are finding. These eigenvectors, eigenvalue will be by theory now it will be like this only. So from this matrix you can extract this, take log, okay, and find out now imaginary part of this, what are now this one. Okay, you can take out lambda and lambda 2. Okay, lambda obtained by taking the logarithm of the eigenvalue of B tilde and now dividing by delta t. So this matrix, once you B tilde have now, we can get this. Okay, there will be simply eigenvalues of e power lambda t, lambda delta t, e power to lambda t, eigenvalues this one. Delta t is the sampling period. Okay, so little mathematical, but this now you already got the answer here. But when we go for DMT, okay, dynamic decomposition, which I'm going to tell, will be B is a huge matrix with a low rank. That case we'll go for a another matrix. Okay, a little bit initially no difficulty, but this power is very high. So now I am sending it now instead of one frequency, you give me now, you sample say 5 different frequency signal. Okay, 1 second or 2 seconds, and add and give to me. Okay, I need not require a big one few data is enough. Okay, give me. I can tell you now the exact frequency of those data. Okay, without using now DFT, FFT now, I can tell. And DFT, FFT, if you give now your data size is small. Okay, DFT or FFT now won't give exact frequency. Okay, it will spread over several frequency. Now comes to get now. I'm going to that problem now. We can get this from auxiliary equation or differential equation. How will we found differential equation? We can produce now multiple oscillating functions. For differential equation, linear differential equation is something called now auxiliary equation. So you take like this: lambda square equal to W1 square, lambda 2 square, sorry, into this one equal to 0, less 1 this one. Okay, so this differential equation is d power 4 by t this one. This differential equation now, if we solve, you will have now two, I can say, sum of two waves as the solution. Omega now with the frequencies omega and omega 2. So these are different equations we are solving. Okay, your solution will be now so yt equal to some c1 cos omega 1 t plus c2 cos 2 omega t. So that should be the type of now solution you will be getting. Okay, so we are artificially creating that situation. So from this one, you can immediately convert into this matrix equation, and the matrix A is here. The solution is given now like this, and we follow the same argument as this. So this now knowing the differential equation, the discretizing or now putting into state equation form like this. If we solve now, this will be the solution. Wait equal to this one. Again, You have now from this, previously you had now this solution. P per at y 0, P per at is now t equal to 1 delta t you are taking, t equal to 1 delta t you are taking, and this you are y 0, and right hand side is not t equal to 1 delta t, so get like this. Okay, so again we follow the same arguments. Okay, same argument as the previous one. So yeah, this should map this quantity to this quantity. That basically mean P per A delta T is a metric. We should map y1 to y2, y2 to y3, y3 to y4, y4 to y5. We get a matrix like that. Okay, that means P per delta T. I am taking a two matrices now, x1 and x2. P per delta T is a matrix such that y0, y1, y2, y3 is mapped to y1, y2, y3, y4. y1, y2, y3, y4 is mapped to okay y2 this one, and this column is mapped to this column. So E per x1 equal to. So using this one now, okay, these two. Suppose now only data is available to me. If you are giving now y0, y1, y2, y5 to some 2025 data, okay, give to me, I'll make now matrix like this x1 and x2, and I will now find out now which matrix will map this column to this column here, this column to this column here, and its eigenvalues will give me information about now frequency. So that is the idea. Okay, P per now take now t equal 130 this one. So this the I can say the solution. Solution is given by now P per data equal to S2 x1 pseudo inverse. From this one we can now. So this matrix I will create. P per data I can find out given x1 and x2. X1 and x2 are now this matrix. Remember this matrix. Where we are getting this matrix? Okay, for example, here I am going up to y9. So 9 data, y0 to y9. So 10 data. Okay, sampled value of not 10 data only you are giving to me. Okay, assuming now you get it from two different frequencies. That 10 data, remember only 10 data. If you give this 10 data to DFT, they're never going to give now these two frequencies exactly. It will say so many frequencies are there. Now I create this matrix. We call this as now anglized matrix. Special name for this one, but idea is come from now differentiation only. E per delta T, I'll find out. Approximate E per delta T will be x2 into x1 pseudo inverse. Okay, this is basically a least square solution actually. Then once you get this matrix, just now assume this is B and just find eigenvalue. Okay, two eigenvalue I will get. Sorry, in this case, okay, 4 eigenvalues because you are taken a 4, so this will be now a 4 by 4 matrix. Okay, so 4 eigenvalue, but not will be your case now complex only j omega 1 minus j omega 1, j omega 2 minus j omega 2. That way it will come to it's a 4. So now 4 eigenvalues because this will be going to be a 4 by 4 matrix. That actually corresponded to real frequencies omega 1 and omega 2. So thus angle matrices appear in the process of estimation frequency are basically arising from homogeneous solution or differentiation. Not this one. From a differentiation only I am getting to this making this matrices, then I get this one. Anyhow, data you have to be called now anglize. So the process you require for now exact frequency estimation is take data anglize. Okay, if you have original data contain 2 frequency, you should take now idea is very simple. You should have now 4 rows. If you have 8 frequency, you should have now 6 rows. You have to put that way. Okay, then now it will lead to your, for example, I am doing this one. MATLAB now I'm taking this equation. I'm assuming omega 1 square equal to 9, omega 2 square equal to 16. So I can create this matrix. Okay, so there is a matrix here. Okay, this S is equal to omega 1 plus omega 1 square, omega 2 square. This as a 90. So this matrix, if you have now, just find eigenvalue. I go of A. I'm getting A, find the I of A. Okay, it is showing now the real part will be 0. Here now 4i minus 4i correspond to now your this frequency and the carbon 3 frequency. So you get exactly that one. So this matrix carries all the information regarding the frequency of your differentiation. Corresponding differentiation, your solution now actually have two frequencies, two oscillations with the frequencies, angular frequencies, omega 1 and omega 2. Okay, that exactly come from here. Now, this is we are taking a differentiation and solving it. Okay, but we do other way. Okay, probably I'll skip this one. We do other way. We take data. We take data from that matrix. Okay, from that matrix, then solve it. 1 second. Okay, so previous methodology only. Just not showing because it may take time to explain the code. Okay, so what I have done now, I used two methodology for estimating the given data. This one is straightforward. I'll go back because here I told I can use two methodology. One, B equal to straightforward like this. Second thing, I can create something called a B tilt. Okay, then again find. Usually B tilt give a better accuracy than the other one. So two-way I'm creating it. I'm not going to the details. Idea is very simple only. Creating that x augmented 1, then getting the answer. Okay, actually my data is generated using frequency 3. Angular frequency now 3.11 and 1.21. So one method using straightforward pseudo inverse, no slight accuracy difference is there. But here, second method using B tilt. This is based on B. This is based on B tilt. Slight changes there in the formulation. Okay, second formulation gives now exact one. So this solution here, when you are creating, I'm assuming frequency is 3.11 and now second frequency is angular frequency is 1.21. Angular frequency this one. So this frequency I'm creating now two signal. Note this one. You try with the FFT. Unless you take an extremely long signal, you cannot tell me that the actual frequency used in that two signal. Sorry, one signal composed of two frequencies is this one. FFTs and DFTs out of question actually to get that accuracy. Now here this is close to the answer, and this one, second methodology. One is based on B e power 30, other now B tilt, right change in this one. You exact. There is I can say this one here. So you try with the FFT, you will never get this exact frequency. You can try because we have time. Okay, so that is now the main part. Okay, then I'm about to finish. So this will give some idea about what the methodology used here. Give some idea about what is happening behind something called your DMT, dynamo decomposition, one of the extremely powerful tool. Okay, so idea is this one. You have now a spatio-temporal data. For example, you assume this data is something like this from a satellite. Okay, from satellite.
Sir, hello.
Yes.
Sir,
Yes.
sir, shall we take two more questions from here?
Yes, sir.
Actually, yeah. There are two more hand raises there. Meenendranath, you there? Or Ronaldo Anuf, both put hand raised. Is there any questions?
Any question from this side? You can.
Yeah, yes, Ronaldo. Yeah, please.
You can continue, sir.
pH temperature பண்ணலாம் pH side சென்சார் பண்ணீங்கன்னா temperature பண்ணலாம் temperature க்கு 0.5 mg.
Is anybody is talking? Ronaldo is there or?
Sir, you can continue.
Yeah, okay. Sir, please continue, sir. Yeah.
Okay, so basic idea in DMD is you assume the data like this from satellite daily basis. You are taking picture of a region daily basis. So you get an daily basis images. And now this image is changing over time because you are taking daily. There will be some changes to that image. Okay, now assume now that image size is 100 by 100. I'm taking a real, not a real image. It will be usually 1000 by 1000 that range only. Say 100 by 100. Okay, so 100 by 100 image, you are vectorizing it, called as now small x1. Okay, small x1. Second day, you take this data, vectorize now, you make it as a single column. Say column you append, each column you go and append and make it a single column like that. Each of this one images you are vectorizing. Okay, something like this you are taking, or probably for 1 year, because you know after 1 year you should say till almost now same situation will come. So like that now your data is coming, you are getting like this. Okay, then x dash. So basic idea is now you are asking the question. Okay, you are thinking x1 x2 as now state variable. Now 100 by 100 matrix. Okay, this 10,000 variables are changing over time. This is the biggest change. Not like now differentiation where now you have 2-3 variables. Okay, each pixel corresponds to a variable now. Daily now that pixel value correspond to location now is changing. Okay, so that is the in data science now. So your number of variables now has gone to now 100 by 100 mean now 10,000 variables x1. It is now changing to x2. Next day it is changing to x3 extra. Okay, we are asking indirectly now what is the matrix A, which is basically e power a delta t. Okay, delta t is now 1 day here, which maps x1 to x2 approximately, x2 to x3 extra. Only thing we are assuming now is a system is not sort of not linear, but now we can also handle non-linear, which I'm not going to ahead on today is this one. So basically, you are asking, okay, what is the differentiation followed by your state variable, or in discrete format, what is the matrix A which maps x1 to x2, x2 to x3. So to do that one, you create x matrix and already x dash this one, and ask the question, which matrix A, which is now it should be now your S1 is okay 10,000 100 by 100. So A should be now 10,000 by 10,000 matrix. That also square matrix only can operate on this one. So which matrix A, which operate on x1, create x2, x2 from x2 you operate on x2, x2 should be equal to x3 extra. You're asking this question to get a approximate now it's a least square solution. We are creating x and x tilt and asking the question now. Note this one, x2 is coming here. Ax approximately equal to x dash. What is this A? But now A is 10,000 by 10,000 matrix. You cannot deal that one. So there comes now in the previous this one I didn't say used a second method where now I am assuming okay the matrix is very huge and now rank is low, maybe 100 instead of this one. Okay, so if the rank is low, suppose the rank is 100, what I require only now 100 eigenvalues and 100 eigenvectors of that matrix A. If I get that one now, I can get the dynamics. Okay, I can tell now actually it is equal to now I am solving the entire differentiation. I'm getting the differentiation, which can be used for prediction of the different tasks now we can utilize. To understand that one now, I'm going a little bit to something called POD to understand DMD better. The POD is not something to do with the DMD, but this will give some idea. POD, proper orthogonal mode decomposition. You get like now your data vectorize this, data vectorize like this. Now this put together, you got X. Then you have now singular value decomposition. You have U sigma V transpose. Your rank is say 100. Okay, you need to consider only 100 columns of U and 100 rows of this one and 100 diagonal elements of this one. Probably your matrix can be what 10,000 by whatever. This now 100 by 100 by depend upon now how many columns you have taken and the column size, whatever. So use sigma V transpose, which now we can interpret this way. This is very important thing. You have here sigma V transpose and combining as now rows. So this matrix can be written as now rank 1 matrices. Use sigma to now one column you take, one row from here, multiply. So this is basically your spatial thing, because this we are converting the column. So this is your spatial information. This is not time evolution or no of the that now this image. You can think of now this image is something like this, and over time it is varying. That is now that how it varies is given here. This one. So this vector here now I'm putting here. So rank 1, several rank 1. So I can call each of this image and this one as one mode and evolution. So mode 1 is this. You reshape it to a matrix and now multiplying over time. Time now so 1 t equal to 0. You multiply, so its amplitude changes. This one. So over time now based on this, okay, this matrix is changing. So we can now a first mode is changing over time. Like that now last mode is changing over time. So this way we can visualize. This is simple singular value decomposition. But this is not DMT. DMT is about now you can operator. So if the we not this case POD, if you take this fluid data and apply the same methodology, you will be getting something like this. This is the mean, some spatial scale, okay, low frequency, little higher frequency, little higher frequency, little higher frequency, now spatial frequency, your dynamics. So dynamics nothing but here, each rank 1 matrices, okay, and vary over time. But you can see a scale there, scale of changes there. It vary or slightly change over time each of this one. You can think of that way. So type image. Okay, but here in DMD now, it is the here now POD taken data. We are assuming there is a dynamics, okay, which is actually captured by a matrix A. You can think of this way: A operate on your data is a vector AX. A again operate on AX, A square X, something like this. Okay, so my aim is if A is known, okay, finally your you can write like this: A equal to A square matrix phi sigma phi inverse, okay, and A power kx. Okay, using this one, you will get like this, and this sigma for k is there. Probably if sigma is like this now, this sigma k you may write as now e for just for an incorporating time e for omega 1 delta t. You can think of now this sigma 1. Sigma 1 equal to like this. It's just mapping only. You can find out now given sigma 1, you can immediately find out given the delta t, what is omega 1 is. So mapping to this one. So once you have this one now, okay, you can interpret this by sigma power b, okay, as something like this. After simplification, for kx, x is now your initial vector over time, okay, because of A operate on continuously, okay, how the modes vary. Mode is nothing but now this phi 1 eigenvectors of now A, phi 1, phi 2, phi n. These are the eigenvectors of this matrix A. I am assuming now A is known, but actual DMT A is not known. So we call this as now A for kx is okay, phi 1. You can reshape it as a matrix, okay, and now we are multiplying with the time varying elements B1 e for omega 1 t, t varies, so the amplitude varies. Here also this amplitude varies over time. Okay, some oscillate in this one, and phi 1 now you can reshape as a matrix. Okay, so this is A is known. Now dynamo decomposition now A is not known. Okay, it is something like this. You have a dx by dt. Okay, it follows a difference equation, but I were assuming now this can be approximated by a matrix AX. This is what we have done earlier. Okay, so from here what we are doing, and here what we are doing is now from the system, we are daily observing data. You can find out now A matrix or corresponding eigenvalues and eigenvectors. So that is the basic idea. Okay, dynamo decomposition is about, there is no time, so I was stopping. Okay, X1, X2. So same thing what I have done now earlier for frequency estimation, same thing. Okay, then we are finding now this A. So instead of finding A, what you are actually using is if I is of very high dimension, we'll be finding something called air tilt. So low dimension, importance of air tilt is now its eigenvalue and original square matrix A, unknown matrix now eigenvalues are same. Okay, not going to detail, but these are small matrix. Corresponding eigenvalue, eigenvector we take and map to original. This one is possible. Okay, so that way now. Okay, this is the once we have air tilt, we again spectrally decompose. From that one now, these eigenvectors, eigenvalue. Okay, we can get the eigenvalue and eigenvectors of now original matrix A, which is 5. Okay, I'm not going to this one. So finally, it is all about getting the eigenvalue and eigenvectors of the underlying matrix A, capital A, not air tilt. Air tilt, they are similar matrix only. So this is what dynamic mode decomposition is doing. Finally, you can express your S of t as now sum of different modes. Okay, not go into detail because of lack of time, but so now this can be utilized for video processing, control system, disease mapping, etc. So you can get the details from the book written by now this person name is Dynamic by Nathan Woods and one more person. You can say Nathan Woods. Just dynamic decomposition. One famous book is there that contain full information regarding this type of applications. Okay, so thank you. So it's basically about from data how to get the differentiation. Instead of getting differentiation, in case of linear differentiation now, you need to get only matrix corresponding eigenvalue, eigenvectors, non-zero eigenvalue, non-zero eigenvectors. Okay, so equivalent to getting a differentiation. Finally, it is that only. Okay, so this I'm stopping.
Thank you, sir. So participants, we can move on to our QA session. So one thing you can done through chat box, you can ask the queries in chat box. Otherwise, you can unmute and speak. There are more hand raises there. Yuchika Amin, you there? Sridevi. So you can unmute and speak. And if you have any questions in this session or doubts.
There is a okay, I can talk. Otherwise, not. I will. I can write here. So there one question is what is the applicability of DMD in life science fields? Already there are a lot of papers DMD applied to ECG signal analysis, EEG signal analysis, and the dynamic mode decomposition. That book now written by Nathan Kutz and this one. Other person name is
Brandon.
Brendan. His wife is working in this neuroscience area. So she has applied. That in different not inside different domain, especially that one. Other thing is now the spread of disease. That is again a biological field. Like that, many field related with now in biology it is applied. Such in run just DMD applications in biology, you will get many papers. We also applied it in spread of coronavirus. Okay, you just type that you will get some papers. Modeling. Another question.
Participants can, if it is more interactive, it will be good. So make a good interactive session at the end of each session. So that's what we needed. So make it more interactive with your queries. If there is no queries, we can. And there is
one more question
is there any
okay.
questions, sir, to your side?
Okay,
actually?
one more is number of measurements required for DMD. At least it will be trial and error, but now requires only, for example, to get frequency. Let's say 4 frequency. Suppose we are putting 4 frequency in a signal. For frequency signal, now you require 8 rows. Okay, so it all depend upon the finally now. In case of real situation or rank of the matrix, it will be trial error you have to utilize for deciding the number of measurements. I think there are literature telling that one, the mathematical relationship. For example, we used for now the frequency estimation. Okay, that paper now contained that our now I don't remember exactly now how since I found out those number, but minimal number now compared to other methodology, it requires only very minimal number.
Yeah, I think almost questions are covered, sir, actually.
Okay.
Yep. So we can wind up this session, and we will come back at after 15 minutes at 11 o'clock with Dr. Sunil Matthew from National Institute of Technology, Calicut, for Mathematics Department. So hopefully you will enjoy these sessions. We will come back soon with another meeting link. You can search and you can check the schedule once again and check the meeting link and join on the time. Okay. Thank you. Thank you, sir.
Okay,
Thank you.
thank
Thanks a
you.
lot, sir. Thank you.
Thank you all the participants.